business geology or geoscience more broadly, and specifically the topics of tectonics and climate. So as Cassie said, basically the first two-thirds of this talk, first I'll introduce myself a little bit more in terms of who's in my research group. One of our members, Grace, is right here with us today, sort of what my research group does, and then we'll dive into the tools that my group uses, as well as other groups in the Department of Earth Sciences here at MSU. And then the final third of the talk will be basically careers in the geosciences. I think we probably all have in our head a picture of maybe what a geologist does, but there's actually quite a broad application of potential careers. And that's just sort of to make you aware, also because there's a huge demand right now in our society for geologists, for geoscientists more broadly, both in terms of resources, managing of those resources, from fields from hydrology to GIS and geospatial. Okay, so that's kind of where I'll wrap up today. If you have questions, please raise your hand throughout the talk. If you want to hold it towards the end, you can always go back to a few slides. If there's just something real quick you want to ask, please feel free to raise your hand. So what we're looking at here in this image on the screen is a photo I took a few years back in Tibet. Okay, it's a part of China. And the Tibetan Plateau sits at pretty extraordinary elevations, mean average elevation of about 5,000 meters. So in this photograph, there are actually peaks that get up to about 7,000 meters in elevation, or about just shy of 23,000 feet. Okay? So really high landscape. I'm standing at about 16,000 feet when I took this photo. Okay? So in this image that we have here, this high mountain range called is being actively uplifted through faulting. Okay? There's basically deformation of Earth's crust, and it's lifting rocks up. So that's the broad field for tectonics that I'll go into in a moment, in more detail rather. But also what you can see going on in this photograph is there are other processes that are active on the landscape, right? We have processes such as glaciation, right? Ice, carving, and the landscape that we see today are exposing rock and eroding that rock. There's also rivers, right, that we see in the foreground here meandering, right? That's eroding sediment, taking it downstream off of the Tibetan Plateau. So broadly speaking, those rivers, especially perhaps more so the glaciers in this case, are being driven by climatic changes. So we have this interplay between deformation of Earth's crust, or tectonics, that's raising high topography, and climate. Okay, and so that's where I'm headed for today's lecture. So just to make sure we're all on the same page here, when I say tectonics, I'm talking about deformation of Earth's crust and sort of upper mantle. Okay, and broadly speaking, in the biggest sense, tectonics, the sort of biggest tectonics that we deal with is plate tectonics, right? Where the Earth is basically divided into a series of plates, okay, and that lithosphere is deforming. And it deforms through a number of processes. So in this depiction here from an artist, we have areas on Earth, you can see the top, sort of center of that photograph, where we have two oceanic plates that are actually separating from one another, spreading apart along a divergent plate boundary. Okay, this is what's happening in the middle of the Atlantic Ocean today. We also have areas where we have two continental land masses here actually coming together and colliding and popping up some high topography. You can think of that as the Himalaya. Okay, so the Himalaya actually formed from the collision of two continents that we'll talk about quite a bit today because I do a lot of my research out there. And then we have areas where we have dense oceanic crust that's actually subducting underneath less dense continental crust. That subduction process, which is active sort of in our neck of the woods, at least in our sort of latitude in, say, Washington, the Cascades, Mount St. Helens, okay, where we have subduction of oceanic crust beneath North America, we have dehydration, basically fluids that are coming up, and those fluids eventually lead to volcanism, looks like Mount St. Helens, Mount Hood, and volcanic arcs that we have in the upper hemisphere. So these are pretty large-scale processes, broadly speaking, mountain-building processes. Okay? But as I mentioned, climate has a huge control on the shape of Earth's landscape as well. This can be sort of relatively local, for instance, orographic effects. So here's the west coast, sort of at the latitude of San Francisco in California, where we have warm air masses coming off the Pacific Ocean. Okay, those are going to hit the Sierra Nevada and rise. As they cool air doesn't like to hold moisture, so it rains out, right? And you get a bunch of snow in the Sierra Nevada, and then you have the Great Basin, which is relatively dry, desert-like, behind the rain shadow of the Sierra Nevada. We can also have global scale climate change and periods in Earth's history where we had extensive glaciation. So around here, the most recent would be the Pinedale glaciation, about 12,000 years ago or so. And that's what's shown here, where the ice sheet, we call the Laurentide ice sheet, came down basically from the poles, came down and actually carved areas such as the Great Lakes that we see today. So those are glacial processes that are happening, across this entire continent, climatic processes that are happening versus more local orographic effects. All right. So one thing I'll kind of emphasize today towards the end is I like to think of the world as tectonics and climate and kind of the interaction between the two. But there is some debate in the literature as to whether maybe one is more dominant than the other. And maybe it's a kind of battle of climate versus tectonics. Chicken or egg, what is driving what, right? Because as we raise high topography and say we create a glaciated landscape, that increases albedo and you get a feedback loop. So chicken or egg, climate or tectonics. All right. So in my introduction, kind of mentioned, I'm a field-based geologist. So this means I go around the world to different field areas, primarily actually where there are convergent margins, two plates coming together, or subduction as one plate. So I do a lot of work in Tibet, which is the largest in terms of elevation, highest mountain range on Earth today. Some work in Patagonia. One thing you might notice here is, I'm standing in this photo probably closer to like 17,000 feet. No snow, no ice, dry, right? Because we're on the north side of the Himalaya. Then I'm at sea level, standing on a glacier in Patagonia, right? Patagonia, Argentina is closer to the South Pole, so there's some climatic effects there. I work a lot in California, where there's some rocks exposed in the Central Valley. Grace went with me this past summer there to do some field work. She's doing a research project within my lab group. And also local projects, such as the Beartooth Mountains, the Beartooth Plateau, trying to understand when the Beartooths basically were exhumed and created high topography in the west. This is my so then the two broad techniques. So I'm field-based, and I could go give an entire lecture of what we actually do in the field. But I thought I'd show you today a little bit more of the analytical work that we do to actually study deep time. And so specifically, my group studies kind of two fields. One, geochronology. We break down that word, geo, earth, chron, time, ology, so study of Earth's time. And this technique is basically going out, finding some rocks, bashing them up, bringing them back to the lab, grinding them up further, and extracting specific minerals out of them that have unstable isotopes, right? Things like uranium that will eventually decay to lead. And we can do some radioisotopic dating to determine the age of a rock, the absolute age when that mineral specifically formed. My group also does a lot of thermochronology. So thermochronology is looking at the temperature or the time temperature of extruded rocks. So this can be everything, for instance, when was a rock at really high temperatures within Earth's crust? When did it get to the surface? And then, as it was eroded into this basin, how deeply buried did it get? How hot did that rock get? And so we, today, I'm going to talk mostly, actually I'm going to talk entirely about geochronology and not really go into thermochronology, but I'm happy to answer any questions about it. We can do both of these techniques here at MSU, and there's a number of labs I also do visit as well. So here's PhD students Aislinn Reynolds, Mariah Romero, working on picking these tiny, tiny little grains. These per scale, this is about 100 microns in length. They're tiny. You have to have very steady hands. don't drink coffee before you do geochron. So they're selecting some grains here. And then we can date these using a laser ablation system. We actually just got one on campus, brand new, where we take a laser and basically ablate material and then measure the isotopes that are within those minerals. We can also use fancy microscopes to look at damage within the crystal lattice and the color techniques. So this is my lab group. As was mentioned, right now I have 10 students, 3 graduate students. Mariah's working in California. Chris is working on the rocks near Lewis and Clark State Caverns. If you haven't had a chance, sort of head out towards Whitehall near the town of Cardwell. The caverns are spectacular. Basically these huge caves carved into some limestone. So he's working out there. Pretty nice. Doesn't have to get on a plane. It's been great during COVID. Just drive to his field area. And Spencer is actually working on some sediments that we cored, went out on a boat, basically cored down in the Indian Ocean and brought back to the lab. Okay, so that's part of the project. And then I have 7 undergraduates, including I mentioned Grace. This group is quite diverse in terms of their backgrounds. We have students that are interested, for instance, Ethan in caving. He's currently applying to grad school to go into basically studying how caves are formed, or karst topography. Nicole's into hydrology, wants to go down that road. We've got 2 budding paleontologists. So with my group, I try not just to take those who want to be geologists, right? Obviously, I'm super proud when Robbie's going off to grad school next year. He's going to work on a project in Argentina. It's very geology-centric. Yeah, I try to take just anyone who's sort of interested in learning more about the Earth. And any good field geologist will have solid field assistants. Springer Spaniels are great field assistants. So, all right, let's dive a little bit more into sort of the meat of the topic. So, when I think of geology broadly, I think about what are our contributions to society, right? And we'll talk a little bit at the end, resources, right? Everything from traditional fossil fuels now moving more towards renewable energies, right? And the mining of things like lithium that actually help us to create more renewable energy, right? But for me, I think maybe because I'm an academic, when I think of geologists and what we've contributed, to me it's one fundamental thing, an understanding of time. What is time? What is deep time? How long ago did processes occur? At what rates did those processes occur? And in order to study time, we have to be able to date things, right? So broadly speaking, just backing up for a moment, my group does a lot of sedimentology and stratigraphy. These are going out into looking at sedimentary rocks, basically rocks that are formed from the breakdown of other rocks. Right? And we do a lot of stratigraphy. And what stratigraphy is it's the spatial and temporal relationship between packages of rocks. So if we look at the example here with the Grand Canyon, you'll see basically it looks like a layer cake. It looks like you just baked a cake with different layers of chocolate and vanilla, right? But those different layers, some of them are of one thickness, and there's others that are much thicker, right? There's variations in the rock record. And stratigraphy, sort of a fundamental assumption is that when rocks are deposited, the oldest are at the bottom and the youngest are at the top. And that's true for the Grand Canyon. It hasn't been faulted or formed. And so we can actually look at the rock record in the Grand Canyon and try to correlate it to other rocks around the western U.S. So for example, there's some rocks deposited at the bottom of the Grand Canyon, right about here. There's rocks that were deposited at a similar age in Montana, called the Flathead Sandstone. Those were deposited at similar times, so you can actually correlate them to large-scale processes that were occurring during that time period. So a big part of stratigraphy is this temporal variation, which allows us to actually then correlate rocks that are deposited at the same time. And the subfield of stratigraphy is called chronostratigraphy. Right? The study of the age of strata and their relationships. So I just want to dive a little bit into how this, basically how geological time was established. It's kind of a big topic for a 45-minute lecture or so, but take a stab at it. So when we think about time, okay, before, like today we have all these fancy machines, right? We can take a laser and measure the exact basically isotopic composition of a mineral array, which is pretty cool. It's over far now. But back in the day, and still used today, we can use fossils. And there's this principle called fossil succession, where fossils are found in a basically determinable order. So we have, for instance, at the bottom of this diagram, this is called trilobite here. You can find all over Montana. Cool fossils to find. Some of the earliest forms of life. We can find this fossil, and it exists, for instance, through this series of rocks. This would be the range of species 1. And then it disappears. And there's a whole bunch of other fossils that appear. And then those disappear, and there's a bunch of other fossils, right? So fossils are kind of coming into the rock record, and then they're going extinct. And this was actually first documented in the basically late 1700s, early 1800s. And there's this guy, William Strata Smith, is his nickname for geoscientists. And he was a surveyor, and he worked in a lot of coal mines in England. And during the process of basically digging out the landscape, he noticed that he would see the same fossils again and again, and they were always in the same order. So he used this to create basically the first map of an entire country, in this case England, the first map, or geologic map, based on fossil succession. So he's basically guessing at the different ages of rocks, long before we even knew what radioactivity was. That's really cool. That's cool. That gets me excited. If you're interested in this, even if you're not into geology, I highly recommend. There's a book called The Map That Changed the World. Has anyone read it? Oh, yeah, this is a must. This is I think it's like 2001 or so. Can I assign a book for Text and Critic? So The Map That Changed the World. I'll call up Dean Lee and ask her. Simon Winchester wrote, I think it's about 2001, and it's basically, it's a quest of scientific discovery. Okay? That's ultimately what it is, and this map really did change our understanding of basically our landscape, okay, and ultimately the age of Earth. All right, so today, sort of moving forward, how do we get to today? A little bit of history. Geochronology as a field actually came about before radioactivity, as I mentioned, sort of with the fossil record. But, you know, we can't actually say how early humans tried to start guessing things like, or estimating, I should say, the age of the Earth. Early civilizations tried to estimate the age of the Earth, perhaps looking at basically the duration of, say, a generation of a human. Okay, that was used commonly, sort of as first estimates. There was also in Hindu culture this idea that time and sort of events were relative as to when civilizations became extinct. Okay, maybe there was a rebirth of those civilizations. Physicists tried to estimate the age of the Earth, thinking about the Earth as a hot sphere that had to cool. How long would that process take? And that was really sort of the change from thinking about things in thousands of years to perhaps millions of years in terms of cooling of the Earth. This guy, Walcott, the date there, 1893, he actually went out to the western U.S. and he looked at packages of rocks. And then he looked at the source material for those sedimentary rocks. And he thought, looking at that mountain, how long does it take to erode a bunch of material to make a package of rocks this thick? Okay, so if you think about today, you raft down the Gallatin River, and there's maybe some of your raft guides, or you've been on some of the journeys there, and there's like that one spot where that rock gets you every year, and you have to be careful, right? That rock is there every year. Until one year it's not, it's eroded downstream, right? So thinking about the rates of processes, he was actually able to put together kind of early geologic timescale. And these numbers we now know are wrong, but what's interesting is the relative ratio between, say, the Cenozoic and Mesozoic eras is pretty close to what we know today. But then along came X-rays and the understanding of radioactivity, right, in the early 1800s. So you probably learned about this in various classes, but for instance, here's Henri Becquerel's, he put uranium-bearing salts onto photographic paper and saw that they left an imprint. He actually put an iron cross while between two photographic plates and noticed that there was an imprint left, suggesting that different materials could perhaps shield things like uranium or radioactivity, right? This is sort of the early stages of why we wear lead vests when we go get x-rays, right, for gamma production. Move forward, Marie Curie and her husband Pierre obviously discovered different elements, but more importantly discovered that within uranium-bearing minerals were multiple radioactive elements. And so as we kind of move forward, the idea of radioactive decay, the idea that there's an isotope that's unstable, and that will eventually decay to a daughter product that's stable, came about from Ernest Rutherford in about 1890. Skipping ahead, just for purposes of time, the 1930s, 40s were a huge period of understanding radioactive decay. Of course, the Manhattan Project really led a lot of this in the development of nuclear weapons. Right? Today, what we understand is that we have isotopes such as thorium-232 thorium, okay, that's unstable and will go through the decay scheme you see here, eventually getting to a stable daughter product 208. Okay? And this rate, the rate at which it occurs, is governed by its decay constant or its half-life. Okay? So the various half-lives for different. In my lab, the radioisotopic system that we use most often is uranium to lead. Okay? And what's cool about this is many of rock's minerals on Earth contain uranium. Okay? So things like apatite or zircon, they contain elements such, or isotopes, I should say, such as 238 uranium, which is really abundant on Earth, that will decay to 206 like lead. It has a really long half-life, meaning it hasn't all just decayed away. There's still uranium left for us to measure. And so the principle of radioactive decay is that we measure our parent isotope, we measure our daughter, okay, and it's the ratio between those that determines the date. More daughter product means there's been more radioactive decay. That mineral's probably been around quite some time. All right, so time. I mentioned geologic time. This is the geologic time scale. It's very pretty, multiple colors. The colors actually have meanings. Like when we look at geologic maps, we see the color green. You're probably Cretaceous, there might be dinosaurs walking around. But all that sort of summary of radioactive decay led to this time scale, right? Where we have the age of the Earth back here in the Hadean, about 4.6 billion years ago. And we can go all the way through geologic time to the sort of explosion of life in the Cambrian, those trilobites I mentioned, through the Mesozoic, when dinosaurs existed, into the Cenozoic, where we are at the very top today. So geologists, or I should say even members of my department, other members not necessarily in earth sciences, study different periods of Earth's history to understand tectonic processes, as well as climate. And of course, there's a lot of work done on recent records of climate and how those are changing. One thing I kind of want to point out that's kind of cool as a geologist is you see that these kind of golden spikes along this time scale. They're literally called golden spikes. What they are is when we establish is really where we find sort of a type locality, say the Turonian, that's in Colorado. Blind here, okay, somewhere here. When we find an area of the rock record and we date it precisely, okay, with, for instance, uranium lead record, we actually go out to that locality and drive a spike in. It's not gold, pure gold, okay? But drive a spike into that rock, and that's the type locality where a accurate and precise, hopefully, geologic age has been determined. And that basically marks the beginning of that geologic time period in the rock. So that's kind of a tangent for today. All right, let's talk about some processes. I threw up a quote. Time, to me, is really cool. And the understanding of how we kind of got to understand time is pretty cool. And so what I kind of love about this quote here is that The discovery of deep time, as it says, basically displaces humanity as the center of that universe, right? And it makes us realize that we're kind of just a speck in geologic time, right? And that there are these processes that have been ongoing much longer than we've been around, that are shaping the mountains that we all like to go enjoy and see today. So let's talk about tools of the trade. Okay, so how do we actually study time or processes within the earth sciences? More specifically, how do we study tectonics and climate? So tectonics, which is primarily what I study, I use geochronology. So how does this work? It's kind of nitty-gritty here. So for instance, we have a subduction zone. Along that subduction zone, we have a volcano. Okay? At depth, there's basically a magma chamber. And if we have what's called a felsic or silica-rich magma chamber, okay, that can erupt on occasion and actually bring minerals, basically cool those minerals, crystallize them, bring them to the surface, and erupt them into an ash cloud. Those minerals then deposit in nearby, say, bodies of water, okay, if they're coming through ash clouds, or they can come down the side of the mountain, like what happened with Mount St. Helens in 1980. Okay, they can actually have lahars and debris flows that you don't want to be in the way of, okay, when they erupt, that actually bring these minerals and deposit them into a sedimentary basin. So volcanic eruption is one way where we can cool our magma, basically form crystals, and bring them to the surface very rapidly. We can also erode this mountain, okay, say through glaciers, and actually bring these rocks that are kind of at depth right now towards the surface by eroding the current surface. That makes sense. And so one of the minerals that my group deals with a lot is the mineral zircon. Okay, this comes from silica-rich magma, SiO2. And zircon's pretty cool because it's really robust. Okay, it's an accessory mineral, meaning if you pick up your average rock outside in the rock garden, okay, it will have primarily minerals such as quartz in it or feldsar, but it also has these accessory minerals such as zircon. Okay, accessory meaning they make up basically less than 10% or even less than 1% of the rock. And zircon is really cool because it's hard, it's robust. So it can come out of a volcano, deposit in this ocean, and actually be transported pretty long distances from waves or longshore currents, basically moving detritus around, and actually withstand billions of years of deformation, which is really cool. So some of you, I think, how many of you were at the freshman research symposium when I spoke? Quite a few of you, yeah. Good to see you again. Good to see you closer up. You were so far away that day. I showed you this diagram then. Okay, so a lot of what my group does is reconstruct where the detritus in a sedimentary rock comes from. So this is a little cartoon diagram where, if you can imagine, you have mountains that basically, think of these as they could be volcanoes, or basically they're crystallizing zircon at various times, right? So we have a volcano that was exploding back in the Cretaceous about 65 million years ago. So most of the rocks around that volcano are about 65 MA. And then we have mountains that are, say, 200 million years old, 500 million, it goes on. And so rocks, if you were going to go out to the field and sample most of the ages that you get from that area are going to be 65 million years, right? If you went out to the yellow mountain here, you'd get about 1.2 billion or 1,200 million years. So what my group does is we use this from a detrital perspective, where, say, we go out to a river, okay, and we collect a bunch of sand, we get zircon out of it, we date a whole bunch of those zircons, okay, and we come up with how we determine all the different age populations of that sample. So I use this already as an example, so you guys already know the answer, many of you, okay? But what we're looking at here is an age spectra, usually shown as a probability distribution plot, or a PDP. And we have ages of 65, 200, and 500 MA. So based upon what I showed you in this reconstruction, did the rivers that sourced this sample come from the west, or did they come from the east? Shout it out. The west, okay. They came from the mountains here, because those are the three age groups we see in our sample. pretty fundamental sort of concept for a lot of the work we do with geochrons. So this work specifically, instead of dating a single event, we're basically reconstructing our landscape. What was the paleo landscape? Where were our rivers coming from in deep time? Okay, so this could be millions of years ago. It could be today. You've got Yellowstone and see this on the modern river. So we did this in the Bridger Range. I briefly showed this, but I want to show a few more details. This was an undergrad-led project. These are all undergraduates. They've actually all graduated now. Last one just graduated last month, or last semester rather. But what we did with this project is we went out to the Bridger Range. You might recognize this photograph. It's does anyone recognize this photograph where it was taken in the Bridgers? It is. It's from Sacagawea, right before you. Yeah, it actually is basically at the top of Sacagawea Peak. Highly recommend that hike once it's not snowing up there. Here's the hike from Fairy Lake up to Sacagawea Peak, the high point in the Bridgers. And when you're up there, besides cool mountain goats, you can actually see all the rocks dipping quite steeply, basically off to the east. And this is actually a sedimentary succession that goes from rocks that are basically about 540 million years old, actually earlier in the Proterozoic, all the way through to rocks that are about 110 million years old. Okay? And so what we did is we actually went out with permission from the U.S. Forest Service and sampled a bunch of these rocks to do this type of analysis, to reconstruct where these sediments came from. Okay? And so the lead author just graduated, actually stayed on for a master's and now doing his PhD, but it was an undergrad research-based project. So if any of you are doing research, like you can do this, right? You can publish a paper as an undergraduate. Right? I fully back that as a professor. Big thing. So these are the results of the study. Okay, so I just want to kind of talk briefly about the paleogeography of Bozeman, ultimately. So in the Bridger Range, we have rocks, as I mentioned, that are about 540 million years ago, Cambrian in age. We actually have rocks that are older than that, are actually 1.400 million years old. And then these are in stratigraphic order, meaning these are the oldest rocks found in the Bridger Range, and these are the youngest rocks found in the Bridger Range. So this is in stratigraphic order. So let's kind of flex our brains a little bit. What do you guys notice about the age spectrum here? We're going from 0 to 4 billion, okay? And each one of these is a single sample that has a bunch of age peaks. Do you notice any patterns or changes from the oldest samples to the youngest ones? How about someone on this side of the room? Any patterns? Do all the curves that represent ages, do they all look the same? No. Okay, so that's the first observation. There's change through time. What about this side of the room? Help this side of the room out. You notice, what are those changes? What do samples say that are Paleozoic in age have that are different than older samples? Don't overthink. They're younger. They contain grains that are younger. Okay? So not only is their depositional age younger, but they also contain a bunch of grains that are younger. We can actually correlate these age peaks to areas of North America where we know the age of the rocks. So for instance, any rock on, this is a map of North America, obviously, purple are rocks that were basically crystallized in Proterozoic or the Archean. They're really old, okay? And so you see these samples contain a lot of age peaks of that age, meaning that the rocks reflected in Montana were probably derived actually from the rocks we're sitting on, okay, some old Archean rocks. But as we go up into younger stratigraphy, these 4 samples here, this is actually the peak of the Bridgers. We were actually standing on, we were standing on Three Forks when I took that photo. Okay. You'll notice all of a sudden there's the appearance of this age population, Renville, okay, it's about 1200 to a billion years old, 1,000 billion years old. And then there's also this HP here, which correlates to rocks that were basically forming in Appalachia. So what this implies is that in the Paleozoic, suddenly we had the input of rains from this part of North America into Montana. Okay, and there's debate as to whether these came from big transcontinental rivers, such as today the Mississippi, Missouri rivers, right? And from Montana all the way to the Gulf of Mexico, right? Rocks that we're sitting on now eventually erode and go down Yellowstone, Missouri, Mississippi. Or were they windblown or brought by ocean currents? Okay, so that's kind of the area of active research. And then our youngest rocks contain this HP, which is actually the yellow here. You only find basically along the west coast of North America where we have active volcanoes. So doing this allows us to create paleogeographic maps using geochronology. So it allows us, for instance, here we are in the Richter Range, this top left corner, that sample up there, okay, in there, right? And we can look at its age spectra. Now it's shown as a pie diagram. But you can see pies that look the same, pies that look different, and we can actually start to make interpretations as to what our landscape looked like, when there were oceans in the past versus when there was land, and what were our paleo drainages. So this is just one application of geochronology. Another one that I've worked on is actually dating the timing of when India collided with Asia. Okay, so this is switching gears, a big scale tectonic process. In this case, India collided with Asia to create the Himalaya mountains that we can see today, right? You can see sort of indentures of India. And we can actually use detrital zircons found in sandstones to date this collision. And what I mean by that is the Indian craton is mostly made up of really old grains. Okay? It's a continent that's been around for a long time. It has the ages you see here. Tibet is also made up of old crust that's been around a long time, but it actually has some ages on it that are quite young in geologic time, less than 300 million years old. And so there's a couple studies that were done, where we went out and basically measured a bunch of stratigraphy. So this is just like the Grand Canyon layer cake stratigraphy. And we looked at the age spectra. So again, from 0 to 2,500 million years. And you'll notice at the base of this, I should say, these rocks were deposited on top of India. Okay? And we went out and we looked, and the bottom of that section basically had age peaks that looked Indian. Okay? They looked like they came from the Indian craton, old crust. And then suddenly there was this change where 300 MA, or more specifically, rocks around 90 million years, appeared on India. And so that first appearance of Asian detritus on top of India means that those two continents must have been pretty darn close together, okay? Because how do we get rocks from this continent to this continent, right? You could say, okay, there's some wind, but most of the evidence looks like what we had is rocks from Asia that were basically trapped on the upper plate, or the Asian continent here. And then as India collided, leading edge of India here, these rocks actually basically prograded onto that continent. So we're using the first appearance of various ages in our detrital zircon age spectra here to actually date the timing of when those continents came together. Does that make sense? Cruising? I try to keep it pretty high level for you guys. You're a sharp group. All right, to the climate side of things. Okay. Okay. So with climate, there was a famous paper that I'm showing you right here from 1990 in Nature that basically was arguing what we notice is in the rock record is if we look at age right here from 60 million years ago to the present versus elevation in meters. Okay, right? So here's the present average elevation of the Tibetan Plateau. So this is a NASA satellite image of Tibet, right? Mount Everest would be kind of right in here, certain, right? And this is India, Nepal, Bhutan in this photograph, okay? or the sedimentary, I should say. What we know is that today we're sitting at 5,000 meters elevation. But when did we obtain that elevation? And there's different proxies we can use. Okay, so I'll talk in a moment about stable isotopes. But we can use different proxies. Okay, some of the things that help us are fossils such as leaves, right? Or you see crocodile teeth in rocks that are now sitting at 5,000 meters elevation. Well, we know today that crocodiles don't live up there. Those rocks were probably much lower in the past. So there's been arguments that were made that basically the rise of Tibet occurred recently, basically in the last, say, 20 million years or so. This paper came along and said, now wait a minute. Is it that Tibet rose and that potentially changed climate? So the Tibetan Plateau today, it's considered the third pole relative to the North and South Pole. Its high elevation plateau region actually diverts wind patterns, so like the trade winds. You may have heard the intertropical convergence zone. It actually diverts those atmospheric circulations, and it actually it's quite a driver in probably a lot of climate change over a long period of time. And so this paper came along and said, well, wait a minute, is it the plateau rose and changed climate? Or did climate allow this sort of plateau to rise? So that question of chicken or egg, climate or tectonic. So how do we actually study climate? That was kind of the last little part here. So you've probably all seen this, I'm guessing, high school, probably some of your classes here, right? Short, what I consider short term, hundreds of thousands of years in my world is short, okay, are driven by Blankenich cycles, right? Changes in basically Earth's orbit around the sun and the shape of that orbit, changes in the tilt, whether we're tilting away from the sun or towards the sun. And these all have a periodicity, okay? A lot of these have been related to, for instance, glacial cycles on Earth. But ultimately, these changes in Earth's orbit, or orbital forcing, change basically the intensity and seasonal distribution of the sun coming into Earth. Okay? So we can actually see this cyclicity in the rock record. So in the rock record, if you go out to an outcrop such as this, what you should probably notice right away is it's very repetitive. It's just bed of rock after bed of rock, right? It looks almost cyclic. And these workers actually in South China went out and were able to group, basically you can kind of see how there's these packages of rock, right? And those packages of rock, when they're being positive, the duration of that cyclicity has actually been related to changes in Earth's climate. And basically changes in orbital forcing that cause periods of, say, for instance, more erosion or more ice. And we can see this cyclicity also on longer time periods. That's mostly what I've studied, is millions of years of change versus hundreds of thousands of years. How do we do that? I promise this is the last technical technique that I'll show you today. One of the methods we use is actually using stable isotopes. Okay? So these are isotopes, equal number of protons, different number of neutrons, that do not undergo radioactive decay. They're perfectly happy in their current configuration of electrons and protons and neutrons. Two of the most common ones we use are oxygen-16 and oxygen-18. And these are sort of the main tools, as well as carbon, that we use to actually reconstruct changes in climate. So how this works, and maybe some of you have seen this before, is basically seawater contains both isotopes, okay, oxygen-16 and 18. 18 is heavier, okay, it has more neutrons, 10 neutrons. It is heavier relative to oxygen-16. And so when evaporation occurs, oxygen-16 preferentially evaporates. It's lighter, it's easier to evaporate. You can think of this as if you had like a heavy bowling ball and a leaf, right? And you drop both, or try to throw both, that's not an example. Golf ball and a bowling ball, right? And you try to throw both of them. The bowling ball is pretty heavy. It's not going to go very far. So that's the same thing with oxygen 18. It preferentially stays within the oceans. So when there's evaporation, the isotopic ratio of 18 to 16, okay, will become smaller and lighter as we kind of rain on the landscape here. And those isotopes can then go back to the world's oceans. But what if there's ice? What if we actually evaporate, again, more 16 compared to 18, and then we rain that out in the form of ice, snow that then converts to ice? What this does is it enriches our ice in oxygen 16. It depletes the world's oceans of oxygen 16, so we have more oxygen 18 within the world's oceans. We can actually measure these changes looking at organisms that build their shells, okay, things like coral, for instance, in the world's oceans, and look at their isotopic ratios through time to reconstruct what the climate was like. If the seawater has more oxygen 18, it means there's more ice in the continents because it's holding all the oxygen 16. And so this has been done for the Cenozoic. Okay, if we just focus on the left side of the diagram here, looking from 70 million years ago to the present, you'll see there's trends. These are based on forams, basically looking at their isotopic compositions of other tests performing them. And you can see this kind of pattern. Here's this long-term kind of global cooling that we had from about 25 million years ago to the present. And so there's this long-term cooling, and the question is that being driven by, this is longer than language cycles, right? These are millions of years, not thousands, not hundreds of thousands. And so this paper in Nature, which is a great, fun read if you I know you have so much time with all your classes to read these type of papers, but this was in Nature, meaning it's really short, which is awesome. And it actually tries to interpret, what's causing these excursions, these isotopic excursions. And what you might notice here is they plotted, for instance, the Tibetan Plateau accelerating its uplift, which also corresponds to a change in climate, to more and more ice, okay, through time. All right. So this can actually be applied. I'll just show you one case study here. This is, again, looking at Tibet, and we're sitting at about, really high elevations, okay, about 12,400 feet. And in these rocks, there are old soils, and these soils contain carbonate. Carbonate is material that is rich in oxygen isotopes that we can document. And so there was a study that actually went out by my friend Ryan Leary here, that looked at the isotopic composition of these rocks. These rocks were deposited about 20 million years ago or so, or 17 to 20 million years ago. And not getting bogged down in the details here, but comparing oxygen and the carbon records, okay? This is modern marine values for reference. What he got, these values of down here of like -10, for instance, in carbon base, they tell us that these rocks that were deposited in Tibet, these old soils, about 20 million years ago to 17 million years ago, were probably sitting at pretty humid, hot conditions. Humid, lots of rain, hot, not the high elevation polar plateau of today. So this is evidence that back in the Miocene, we were seeing at low elevation, and somehow we have to get to modern elevations since then. All right. So last example here is, I've been talking mostly about deep time, millions of years using geochronology as well as stable isotopes. There's a lot of work on campus and more recent climatic changes over the last few thousand years. So this is from my friend and colleague Dave McPuffy and his PhD student Pico Alt, who did her master's here and now is working on her PhD. And she actually looks at pollen. Okay, so she goes out and cores, you can see her and Dave here, for instance, coring Twin Lakes in Montana, looking at the pollen that's in those sediments. They do this over in Leon Johnson Hall. And relating those pollen that you see here back to specific types of, say, pine trees, specific trees, shrubs, and herbs. And what they notice is round about, say, 9,000 to 6,000 years ago, see how the green kind of drops off there and then comes back? There's basically a drop in our pine tree species while there's an increase in our shrubs like armesia, that we see up here. This change in reduction of pine and increase in armesia is related to basically warming or drought. Okay, pines don't like drought. And so this is basically a pretty drastic change that they've been able to document, and others have documented, looking at basically the effects of increased warming about 6,000 years ago. So if you're interested in recent time, there's plenty of people on campus that do that type of work as well. Okay, so I'm just going to finish off here about 5 minutes. Okay, thanks for bearing with me. Don't start. About careers in the geosciences. Well, maybe we'll just save questions to the end. So hopefully you're reading this comic. Continuing to listen to me babble on. A lot of what I presented today seems probably quite academic, right? And that's okay. I have a huge passion for understanding the past history of Earth. From that, I have many colleagues, and many of my students go on to, say, future climate or tectonic modeling predictions. And that can be in the realm of tectonics, right? Thinking about things like earthquakes, seismic hazards, or that could be in, for instance, the realm of climate. But not everyone's going to be a professor, right? So what can you actually do with these skills? So as a geoscientist, there's a breadth of jobs that geoscientists do, okay? Perhaps the one that jumps out maybe most readily is you think geologist and you might think oil and gas, right? Petroleum industry. And that's true. That's been true for the last 30 years or so. Many of our students still go in that direction. Many of our students have transitioned within the energy industry to be more into renewable energy. And this kind of falls within mining. I don't know if you know this, but Montana is the only exporter in the US of palladium. Anyone know what palladium is used for? Where are my engineers at? Catalytic converters, right? We need those to get rid of some of the toxic stuff out of our cars so that we're not releasing as much toxic chemicals as we could. So you're still releasing CO2. But that's a huge export from Montana, and that comes from the earth. That comes from mining. Lithium, right? You want to own a Tesla? Probably not. It's way too expensive. I can't afford one. But, okay, lithium batteries, right, come from mining. And so as we shift, perhaps from fossil fuels, mining is still a very important part of the renewable energy development. We also have students that go into environmental consulting. This can range from jobs. I have a former student who literally does soil sample cores at an airport to study the runway to see if it's strong enough to basically land not only airplanes but spaceships. Okay, so I should say that, not spaceships. So I just went totally like spaceships, like the Enterprise is landing. Shuttles, space shuttles. Okay. Ooh, that'd be exciting. The Enterprise shows up. So, okay. Hazards is a big one, obviously with things like earthquakes, hydrology, booming field. I can't tell you how many emails I get, probably about once a week, from a hydrology company asking me for geologists, not just hydrologists, okay? Paleontology, obviously a museum of the Rockies. Geospatial analyst, and so on. So I just want to show you 3 quick examples here. I have a friend, Nora Nominski, that these are actually from her Instagram page. Pretty awesome. Her Instagram is way cooler than mine. She works for the Monterey Bay Aquarium Research Institute, MBARI. This is an organization that was actually founded by David Packard, so he used his affiliates, to actually set up a scientific research center off the coast. So this is San Francisco is just off the screen. This is Monterey Bay, if you've ever been to the aquarium out there. It's actually the continental shelf going into the deep marine environment. This organization, maybe there's a few biologists, budding biologists, ecologists in the room, they do everything from studying basically zooplankton, or I should say more broadly, they're looking at life at the bottom of the ocean floors. My friend Nora is a geologist. She gets to drive these types of submersibles. She actually got to go down in one, which was really awesome. And she actually went out and put up these cores, and she's studying the mud that's around, like this is a new sea cucumber they discovered. This cucumber, there we go. Okay, she's studying the chemistry, the geochemistry of the mud that's housing this new form of life. Okay, so she's a geologist, not a biologist, but she's working with biologists. All right, you can be an astronaut. So what's pretty cool is recently, starting with the class of 2017, you'll see Dr. Jessica Watkins here. She did her undergraduate in geology as well as her PhD. And she was selected for the 2017 astronaut class, the first class to kind of be targeted for future Mars missions. They specifically were targeting geologists, and that's because if you look at the surface of Mars, here's a photograph from NASA from the Curiosity rover from a few years back. You can pick out the layers of rock here, right? Sedimentary rock all over Mars. So they're interested in sending astronauts with various skills. Okay? One of those being interpreting the rocks there and perhaps where you might find life based on the composition of those rocks, things like silica and stuff. She's a really awesome lady, so look her up if you like. And the final example I'll give is jobs within geospatial analysis. Do you have anyone who's perhaps taken Geography 284 GIS in the room? Okay, has anyone taken a GIS class? Okay. Are you all humanities majors? Okay, that's cool if you are. Even if you're in humanities, right? What GIS is, it's referred to Geographic Information Systems, okay? This is using techniques such as satellites, or in our department, UAVs, most commonly called drones, okay, to actually map out different features. And these can be features such as Dr. Laskowski, who's a professor in our department. He has a thermal camera. He's out near Norris Hot Springs. He's trying to understand why there's hot springs there. Okay, they're not part of the Yellowstone system, so why are there hot springs there? What's governing that? We can use in this case, Andrew Mullen, who just defended his master's yesterday, also did his undergraduate here. Snow scientist, he's trying to understand basically the effects, different effects of snowpack and how depths kind of change. And so traditionally this is done using satellites, but those only have a certain resolution, right? So a drone can get you even higher resolution at a given point. You've got things like snowpack thickness and predictions for snowpack, water resources. Broadly speaking, GIS, if I could give like one piece of advice for students in college, it would be to take one GIS class at least. Okay, it might seem a little intimidating. It's a lot of sort of computer work, right? And you're like, no, I want to be outside, or I want to do this or that. But it is an amazing tool we have. We're using imagery from satellite data. GIS is what's used to plan cities. Okay, so planners use this when they're planning how to lay out cities. GIS and spatial analysis was done on 19th Ave before Target and Walmart and all those got put in. Okay, so it has applications kind of across the board, and it really is sort of at the forefront of when we look at big changes, both at human timescales, human migration, as well as longer systems such as geothermal systems. So Geographic Information System, this is one of the biggest employers of geoscientists today coming out. And you don't need a master's or PhD to actually do quite well with GIS. So I'm happy to answer more questions on that if you have it. And we'll wrap up there, because I know it's getting late, and that was a lot of information.